Integrating free-form memory and quantum optical processing in future computers. Introduction. Modern computing is on the cusp of transformative changes, driven by the need for ever faster processing and new paradigms beyond classical electronics. The rise of data-intensive applications and AI has pushed conventional CPU-GPU architectures to their limits. In response, researchers are exploring exotic concepts such as free-form memory, a speculative memory paradigm not bound by traditional ROM/RAM constraints, hybrid quantum classical processors, and photonic, light-based, computing. These emerging ideas promise to overcome current bottlenecks, from memory bandwidth and latency to parallelism and energy efficiency. This paper surveys the possibilities of such an advanced system, one that might incorporate a quantum cycle alongside a conventional electronic cycle, ultrafast light-based interconnects, and self-optimizing behaviors. We discuss theoretical underpinnings and practical considerations, drawing on the latest research in quantum computing, optical processors, novel memory technologies, and dynamic system management. Free-form memory, beyond conventional ROM and RAM. Free-form memory is an abstract concept that extends beyond read-only memory, ROM, and random access memory, RAM, as we know them. In a classical sense, ROM holds fixed data permanently, while RAM allows flexible read/write but is volatile. Free-form memory, as imagined here, could be a memory form that exists dynamically in spacetime, perhaps storing information in ephemeral physical states that cannot be revisited once released, analogous to a one-time event. Whichever point in time and space existed, it is just a spacetime quirk or anomaly. It can never be reaccessed once ejected, as the concept suggests. Intriguingly, this description aligns with the behavior of quantum memory. A quantum memory stores qubits, quantum bits, without collapsing their superposed states, but any measurement, readout, irreversibly destroys the original quantum state. In essence, a quantum memory is the quantum analog of RAM, holding a superposition of 0 and 1, and even entangled states, until observation. Once observed, ejected, the information is fixed to a classical value and the prior quantum state cannot be restored. This property mirrors the ephemeral use-once nature attributed to free-form memory in our scenario. From a practical standpoint, quantum memories are an active research area due to their importance in quantum computing and networking. They must maintain quantum coherence, delicate phase information, as long as needed, isolating the data from environmental noise. Current implementations, e.g. ensembles of atoms or rare earth ions trapping photonic qubits, can store quantum states for brief durations, milliseconds in cutting-edge experiments. The fragility of these memories means they behave almost like a one-time ROM. Reading them gives a result but collapses the stored superposition, after which the exact original state is gone. In a future free-form memory module, one could imagine a bank of quantum memory or other exotic memory, perhaps based on holography or spacetime effects, that the system can draw upon for extremely high throughput, parallel data storage, but which must be used carefully since any retrieval might permanently alter the content. Apart from quantum mechanisms, another interpretation of free-form memory is optical or photonic memory, which stores information directly in light. Storing light is challenging. Photons don't sit still easily, but progress has been made using optical delay lines, loops, and bistable photonic devices. Optical random access memory, ORAM, research has demonstrated bit-level optical storage cells and even optical RAM prototypes. The appeal of optical memory is ultra-fast access and bandwidth, and seamless integration with optical data links. By keeping data in the photonic domain, one could borrow memory at light speed, minimizing electronic bottlenecks. Indeed, recent surveys highlight that optical memory and interconnect advances aim to tackle the CPU memory bandwidth bottleneck in computing by using light for both carrying and storing data. In a free-form memory scenario, the system's RAM and GPU could dynamically share a unified photonic memory pool. Such a pool, not being fixed to one device, acts like a fluid resource. Whichever component, GPU or CPU/RAM, needs it can claim it, akin to dynamic memory allocation on hardware. This concept is reminiscent of unified memory architectures in today's heterogeneous systems, but at a far grander scale and speed. For example, emerging research on disaggregated memory in data centers proposes optically connected memory pools that any compute node can access with minimal latency. A free-form memory might similarly be a disaggregated, light-linked memory accessible to CPU or GPU on demand, effectively eliminating the competition by making bandwidth virtually at light speed. Technologically, achieving this would require programmable optical memory hardware. There are promising steps. A recent demonstration of a programmable photonic memory latch showed fast, scalable optical storage using integrated photonics. Moreover, a comprehensive review notes that photonic integration has brought optical bit storage from a curiosity to a realistic prospect, with volatile optical SRAM and DRAM analogs under development. These could one day serve as true RAM replacements. In summary, free-form memory, whether interpreted as quantum memory or optical RAM, represents the frontier of memory technology. It offers a vision of memory that is ultra-fast, parallel, and possibly transient, augmenting traditional memory for specialized high-throughput tasks. However, harnessing it will demand new control logic to manage its ephemeral nature and coordinate which subsystem, CPU or GPU, controls it at any given moment. Quantum classical dual processing cycles. The next concept in this futuristic machine is a processor that has two cycles, a quantum cycle and a conductive, classical, cycle operating in tandem. In practice, this refers to a hybrid quantum classical computing architecture, wherein a quantum processing unit, QPU, works alongside classical processors, CPUs/GPUs. Rather than a single processing loop, computation alternates or intertwines between quantum operations and classical electronic, or optical, operations. This idea is already present in today's research. Many algorithms like the variational quantum eigensolver, VQE, and quantum approximate optimization algorithm, QAOA, are inherently hybrid, consisting of iterative loops that switch between quantum computation phases and classical processing for feedback or optimization. In such algorithms, the interplay is tight. The classical computer sets up parameters, the quantum processor executes a quantum circuit, entangling qubits, evolving superpositions, returns a result, and the classical side processes it and adjusts for the next quantum cycle. Essentially, the system ping-pongs between quantum and classical cycles until a solution converges. This is exactly the kind of dual-cycle operation envisioned. The quantum cycle would involve operations like superposition and entanglement in qubit registers, perhaps leveraging the QPU's ability to explore many states in parallel, while the conductive cycle refers to standard logic operations likely running on light-based or electronic circuits, the light GPUs and CPUs mentioned. The two cycles must remain synchronized through some coupling. The prompt uses the term connect through induction, which we can interpret as a signal coupling or control feedback linking the quantum and classical domains. Current efforts in quantum classical integration corroborate the feasibility and challenges of this dual-cycle approach. Surveys emphasize that quantum computers are not standalone replacements for classical computers but accelerators to complement them. The most promising vision is to treat QPUs as specialized coprocessors, analogous to GPUs, within a larger system. For instance, in a high-performance computing (HPC) context, a QPU might be embedded on the same node or board as CPU and GPU, directly interfaced via high-speed interconnects. In that tight integration model, the QPU becomes another compute unit triggered during its quantum cycle, then handing off results to classical units for the conductive cycle. NVIDIA's CUDA Quantum Initiative and others are already exploring programming models to dispatch work to quantum coprocessors in a manner similar to GPUs. One critical requirement for such dual-cycle operation is low-latency communication between the quantum and classical parts. Each cycle may only be effective if the overhead of switching contexts, sending data to the QPU, waiting for a quantum operation, retrieving results, is minimized. Researchers note that interfacing HPC and QPU hardware is not straightforward. Current quantum devices often sit remotely behind cloud APIs, loose integration, incurring significant latency. The push now is toward tighter hardware integration to make quantum classical data exchange as fast as possible. This might involve specialized shared memory, perhaps where that free-form memory could play a role, buffering data between cycles, or high-bandwidth links, potentially optical fiber or superconducting links for cryogenic QPUs. A recent survey stresses the need for standardized, high-speed interfaces to achieve low latency and high-bandwidth interconnection between quantum and classical resources and unlock the full potential of QC as an accelerator. In effect, the quantum and classical cycles must be inductively coupled like gears, each cycle triggering the other in rapid succession. During the quantum cycle, the system leverages quantum phenomena, superposition, where qubits can represent multiple values at once, and entanglement, where qubit states are correlated across distance, to perform computations that would be inefficient classically. This might involve, for example, exploring many computational paths in parallel or modeling quantum mechanical systems directly. The classical, conductive, cycle, by contrast, could be a high-speed conventional logic cycle, possibly running on an optical CPU/GPU that processes the results of the quantum step or prepares the next quantum inputs. Induction in this context could also imply using electromagnetic coupling or analog signals to quickly transfer states. For instance, some proposals consider microwave or optical signals to link superconducting qubits with room temperature electronics. While speculative, one could imagine a QPU that communicates via photonic signals to an optical CPU, thereby both operating at light speed domains. In summary, a dual-cycle quantum/classical architecture is a theoretical framework for hybrid computing that many researchers are pursuing in simpler forms. The quantum juxtaposition of cycles mentioned is essentially the state-of-the-art goal, a harmonious system where quantum processors work side by side with classical processors, each doing what it does best. Achieving this outside of theory will require significant innovation in hardware interfacing, coherence preservation, and programming models, but early hybrid demonstrations, e.g. small QPUs integrated with classical control for iterative algorithms, are validating the concept. Photonic processors and light-speed interconnects. To make the above system viable, especially the notion of bridging throughput at light speed between components, photonic computing and communication are indispensable. The conversation alludes to light GPUs and CPUs, which refers to processors that use light, photons, instead of electricity, electrons, for computation. Photonic processors have seen rapid developments recently. In 2025, two photonics companies demonstrated breakthrough chips, one solving complex optimization problems and another running neural network models, tasks once considered out of reach for light-based systems. Photonic computing inherently offers massive parallelism and bandwidth. Photonic computing uses light to perform computations, promising faster analog processing with lower energy. Because light waves at different wavelengths can pass through the same channel without interfering, a photonic circuit can perform many operations simultaneously. Wavelength division multiplexing is one example, unlike electronic circuits where signals must avoid interfering. This parallelism could be crucial for handling the throughput from free-form memory or rapidly exchanging large datasets between CPU, GPU, and QPU. One concrete example is Lightmatter's recent photonic processor. It incorporates photonic tensor cores to execute matrix multiplications for AI models entirely with light, controlled by interfacing electronic chips. In doing so, Lightmatter showed that you can build a computer that's not based on transistors and run state-of-the-art workloads, ResNet, BERT, and other neural networks, with high efficiency. Such a processor can be viewed as a light GPU, massively accelerating parallel math with minimal electrical delay. Another company, Light Intelligence, built a photonic computing engine to solve Ising model optimization, running certain problems 500 times faster than a modern GPU by exploiting optical parallelism. These achievements underscore that optical processors are moving from theory to practice, targeting precisely the kind of high-throughput tasks that our hypothetical system demands. Equally important are the optical interconnects, the highways between components. In our scenario, to bridge throughput in a way that is pretty much light speed, the connections between memory, CPU, GPU, and QPU likely need to be optical or at least extremely high speed. A major performance limiter in today's computers is not raw compute speed but data transfer delays and energy cost between chips, the so-called memory wall. Photonic interconnects can alleviate this. Nicholas Harris of Lightmatter notes that in modern AI systems, even an infinitely fast processor yields under 2 times speedup because the system waits for data most of the time. To address this, Lightmatter's design integrates a digital interface with the photonic cores to ensure fast, efficient communication between components. This highlights a general principle: a cutting-edge processor must be co-designed with equally powerful data links. In research, optical I/O and memory buses are being developed to replace or augment electrical ones. Silicon photonics enable onboard optical interconnections that significantly boost bandwidth and reduce latency and power per bit. For instance, experimental architectures use optically connected memory modules, allowing memory to be physically separate, disaggregated, yet communicate via fiber with negligible speed loss, improving scalability and bandwidth. There is also progress on optical RAM, as discussed, which would let memory and interconnect all operate in the photonic domain for coherence. Overall, the use of light-speed interconnects in our proposed system would ensure that the CPU, GPU, and free-form memory can share data without the usual bottlenecks, effectively operating as a single coherent unit despite being distinct components. One challenge of photonic computing is that analog optical signals can be noise-prone and require calibration for long calculations. Solutions like active calibration and specialized numeric formats, e.g. adaptive block floating point for photonic AI cores, have been introduced to mitigate errors. This indicates that while optical processors and links are fast, system designers must include error correction or adaptation to maintain accuracy, particularly important if these form the backbone of memory and CPU communication in a critical system. Nonetheless, the energy efficiency and throughput advantages are compelling. Photonic systems can achieve orders of magnitude improvements in performance per watt for certain workloads. In the context of our dream machine, one might envision an optical CPU/GPU handling routine tasks and massive data movement, feeding a QPU when quantum computation is needed, all tied together by a web of fiber optic or on-chip waveguide connections. Data would effectively travel at the speed of light within the machine, ensuring that even if, say, the GPU hoards most memory bandwidth, the RAM, free-form memory, can still supply data to the CPU without undue delay. The bandwidth is so high that contention is minimized. This architecture could, in principle, operate at light-limited speeds, meaning the only latency is the physical time of flight of signals, nanoseconds across a board, not circuit switching delays. Dynamic thermal management and self-repair mechanisms. High-performance systems that push into new domains, quantum and optical, will face significant thermal and reliability challenges. The conversation suggests an almost biologically inspired response. In emergencies only, the CPU might overclock itself and perform self-repair, borrowing thermal headroom from other components, like a GPU or even the display output, and using any available cooling capacity. While this sounds futuristic, analogous ideas exist in today's research. One is the concept of computational sprinting, where a processor is designed not just for steady-state performance but for short bursts of extreme performance exceeding normal thermal limits. For example, in smartphone chip research, engineers have proposed activating many cores at once for a brief sprint to finish a task quickly, generating heat faster than the device can normally dissipate, then idling to cool down. During those sprints, clever techniques like on-chip phase change material heat sinks can absorb the transient heat spike. This is akin to an emergency mode overclock. The system leverages thermal inertia to momentarily boost CPU speed, or number of active units, beyond sustainable levels. A similarly managed sprint in our advanced computer could allow the CPU to handle a critical computation by throttling down other heat-generating parts, GPU, etc., thus reallocating power and cooling to the CPU. Indeed, dynamic power allocation between CPU and GPU in a shared power envelope is an area of active study, aiming to intelligently distribute power to whichever component needs it most for the workload. By borrowing from the thermal displacement of an idled component, meaning using the slack in the cooling system when, say, the GPU is inactive, the CPU could achieve higher clock speeds temporarily. This kind of cooperative thermal management has been demonstrated in heterogeneous systems. For instance, some laptop designs use a feature where if the GPU is idle, the CPU is allowed a higher turbo boost and vice versa, all within the same total power budget. Academic research confirms that such dynamic thermal management can significantly improve performance under power constraints. Another forward-looking aspect is self-repair or self-healing of the CPU under stress. Fault tolerance is crucial as we push hardware to extremes. Notably, engineers at Caltech have already developed prototype self-healing circuits that can detect failures in transistors and reroute signals to work around damaged areas. In one experiment, a chip with over 100,000 transistors was deliberately damaged with a laser. It reconfigured its internal pathways and continued functioning, guided by an on-chip algorithm that learned which parts were broken. As Ali Hajimiri of Caltech put it, microchips can now both diagnose and fix their own problems without any human intervention, moving one step closer to indestructible circuits. While these chips don't literally regenerate silicon, they provide redundancy and adaptability, much like a brain finding new routes if some neurons fail. In our advanced system, we could imagine a CPU, or any component, that, when pushed to its limits, thermal or electrical, can adjust its configuration, perhaps disabling certain cores that overheat, reassigning tasks to cooler units, or even reconfiguring programmable hardware, like an FPGA-style approach, to avoid faulty regions. Self-repair algorithms would keep the machine running, especially in critical emergency scenarios, instead of crashing. Combined with error-correcting codes and resilient system software, this could yield a platform that is highly robust, capable of surviving sudden stress or partial failures, an essential trait if we're relying on it for cutting-edge computations. Thermal management may also involve advanced cooling techniques. If quantum processors are involved, some, like superconducting qubits, require cryogenic temperatures, whereas optical and electronic high-performance components may generate large heat fluxes at room temperature. Integrating these in one system could necessitate a hybrid cooling solution, perhaps cryostats for the QPU and liquid or phase-change cooling for the photonic/electronic parts. A coordinated control system would oversee this, deciding when to activate emergency cooling or when to throttle parts to prevent overheating. There is precedent for such coordination. Data centers and HPC systems use dynamic thermal management software that can, for example, migrate workloads or modulate frequencies to avoid hot spots. Future systems might take this further, essentially treating available cooling power as another resource to be allocated on the fly. In essence, the vision is a computer that not only runs fast under normal conditions but can intelligently strain itself when needed, and heal or protect itself from damage in the process. This draws from concepts of sprint computing and self-healing hardware which are being actively explored. Implementing it would require sensors everywhere, temperature, power, error detectors, and an AI-driven controller to decide when to enter emergency mode, when to reallocate thermal budget, and how to reconfigure around any faults. The outcome would be a machine that is extremely adaptive, much more so than today's PCs which rely on fixed safety margins. It would use all available physical headroom, thermal, electrical, to meet computing demands when absolutely necessary, and recover gracefully afterward. Design steps for a hybrid quantum photonic computing device. Bringing together all these advanced components, freeform/quantum memory, photonic CPU/GPU, quantum coprocessor, and smart management is a formidable task. However, we can outline a plausible step-by-step plan for how one might procure or develop the material and components for such a computing device. Each step is informed by current research trajectories, bridging theoretical possibilities with practical considerations. 1. Acquire advanced memory technology. Start by obtaining or fabricating memory modules that go beyond conventional DRAM. This could involve quantum memory units, e.g. a small ensemble of atoms or NV center qubits that can store quantum states, and integrated optical memory chips. The goal is to have a prototype free-form memory, perhaps a bank of high-speed optical RAM cells for bit-level storage, supplemented by a quantum memory for experimenting with one-time storage of qubit states. If off-the-shelf optical memory is unavailable, one might collaborate with a photonics lab to build a programmable photonic memory latch or an optical delay line memory as a starting point. Ensuring these memory devices can interface with electronic controllers for read/write operations is key at this stage. 2. Source photonic processors. Light-based CPU/GPU obtain a photonic computing unit, such as the processors developed by companies like Lightmatter or Light Intelligence, or a research-grade photonic FPGA. If a complete photonic AI accelerator is not accessible, one could use a silicon photonics toolkit to design a simple optical computing circuit, for example, a matrix multiplier using Mach-Zehnder interferometers. The photonic processor will serve as the light CPU/GPU capable of ultra-fast parallel computations. Its role is to handle classical computations and intensive parallel tasks, like AI inference or graphics, with high throughput and low latency. At this step, also secure the necessary lasers, modulators, and photodetectors that the optical CPU/GPU will require for operation and integration. 3. Obtain a quantum processing unit. QPU include a quantum processor to provide the quantum cycle functionality. This might be a small quantum computer or accelerator, for instance, a superconducting qubit system, like IBM or Rigetti's multi-qubit chips, a trapped ion setup, or even an analog quantum annealer. Many quantum processors are available via cloud, but for tighter integration, one might look for a local or desktop quantum device. Companies such as Quantum Brilliance are working on room-temperature mini quantum accelerators, while others provide PCIe card quantum devices for research. The QPU need not be large, even a few qubits that can demonstrate entanglement and superposition would suffice for prototyping the hybrid architecture. The important task is to interface this QPU with the rest of the system, ensure there's a control interface, classical computer or microcontroller, that can send instructions to the QPU and read results, ideally with a high-speed link. In a full build, one would integrate the QPU on the same computing node as the CPU/GPU, treating it as a coprocessor accessible through a common bus. 4. Develop a unified memory architecture. Design the memory subsystem so that the RAM and GPU, and possibly QPU, can share the freeform memory resource efficiently. This may involve a unified memory architecture where all processors address a common memory pool. Concretely, one can set up a high-bandwidth memory, HBM, module or a pool of DDR5 that is shared by the CPU and a GPU, and then augment it with the optical/quantum memory from step 1. Research from the HPC field on disaggregated memory and optical memory interconnects will inform this design. One might use an optical interconnect, like an optical PCIe or custom fiber link, to connect the memory pool to the processors, aiming for light-speed data transfer. The result should allow, for example, the photonic GPU to directly fetch data from the optical memory, or the CPU to offload certain data arrays into the quantum memory for one-shot computation. At this stage, creating a coherent cache system that spans these different memory types is a challenge. It may require custom cache coherence protocols or simply treating the QPU's memory as an I/O device. The focus is on achieving maximal bandwidth and minimal latency between all computing units and the memory, leveraging optical links to do so. 5. Integrate quantum classical control interface. Build the interface logic that coordinates the quantum cycle with the classical cycle. This involves both hardware and software. On the hardware side, one could use an FPGA or a high-speed communication controller that links the classical processors, CPU/optical GPU, with the QPU. The interface must handle triggering quantum operations and retrieving the results into classical memory. Prioritize low-latency connections. For example, if using a superconducting QPU at cryogenic temperatures, use a microwave or optical fiber link for fast signal transmission. On the software side, develop a basic runtime that can dispatch a task to the QPU and pause the classical computation until the quantum result is back. This might draw on frameworks like NVIDIA's CUDA Quantum or quantum programming languages, Qiskit, that support hybrid workflows. The goal is to enable seamless iteration. The classical side should be able to call a quantum subroutine as part of its processing loop with minimal overhead. Achieving this tight coupling is crucial. As literature suggests, the efficiency of hybrid algorithms heavily depend on the quality of the interfacing between quantum and classical parts. Thus, significant testing will be done here to reduce communication delays and perhaps to pipeline operations, perform classical computing while the QPU is busy when possible. 6. Design thermal management system. Equip the device with a robust cooling solution and sensors, laying the groundwork for dynamic thermal management. Acquire advanced cooling hardware such as liquid cooling for the photonic and electronic components, which may generate substantial heat, and a cryocooler if the QPU is superconducting. Additionally, consider phase-change materials or heat reservoirs to absorb burst heat output. For example, attach a small heat sink with a wax or alloy that melts to soak up heat during an overclocking sprint. Place temperature sensors on the CPU, GPU, QPU, and memory modules. Next, implement firmware or control software that can read these sensors and adjust component states, frequencies, power limits, on the fly. This might involve integrating with the CPU's dynamic voltage frequency scaling, DVFS, interface and the GPU's driver to throttle or boost as needed. Initially, one can set conservative thermal limits, then gradually test pushing beyond them in short intervals while monitoring stability. Establishing safe emergency thresholds, e.g. a maximum allowable temperature for short durations, is part of this step. Essentially, this is building the overclock and cooldown infrastructure that later steps will exploit. 7. Implement dynamic power/thermal allocation. Now that the hardware for cooling and monitoring is in place, develop algorithms for dynamic power allocation between components. This could start as a simple policy. For instance, if the CPU is at 100% utilization and the GPU is idle, the system can divert extra power to the CPU, allowing it to raise clock speed or enable more cores. Conversely, if the GPU needs a burst for a graphically intensive task and the CPU is relatively free, shift power budget to the GPU. Such cooperative management ensures no part is a thermal/power bottleneck while another part has spare capacity. Use machine learning or control theoretic approaches to predict which component will benefit most from additional power at a given time. For example, a ML model could monitor the workload pattern and preemptively give the CPU a power boost when a serial section of code is about to execute, reducing latency, then return power to the GPU during parallel sections. This step turns the earlier thermal design into an active system, akin to a car's traction control but for power and heat. It will likely involve iterating on firmware that interfaces with both CPU and GPU power controls, and possibly memory power states. By the end of this step, the machine should be able to engage in emergency high-performance mode safely, e.g. the CPU can exceed its normal TDP for a short time by borrowing thermal capacity from an idle GPU, much as envisioned in the user's scenario. 8. Incorporate self-healing and fault tolerance. Augment the system with self-repair capabilities. This involves two facets: hardware redundancy and autonomic fault management software. On the hardware side, if using an FPGA or a configurable array in the CPU/GPU, design it with spare resources, extra ALUs, extra network links, etc., that can take over if one part fails. Alternatively, use a multi-core CPU and plan for one core to be a hot spare that can replace a failing core. The photonic components might include multiple light paths where if one waveguide is found to be misaligned or damaged, signals can be rerouted. On the software side, implement health monitoring that can detect anomalies, e.g. using built-in self-test circuits or performance counters to spot if a core is misbehaving. Then, implement a recovery routine. For instance, if a CPU core is overheating or giving errors, the controller can shut it down and shift its workload to another core, possibly with a slight performance loss, but avoiding a crash. Drawing inspiration from the Caltech self-healing chip, one can create a simple learning algorithm that tries different routing or core assignments after a fault until the system resumes correct function. Additionally, include error-correcting codes, ECC, in memory and communication channels so that transient faults, like a bit flip from a cosmic ray or a momentary optical glitch, can be corrected without manual intervention. By the end of this stage, the device should not only handle planned stress but also unexpected faults, diagnosing and fixing its own problems without human intervention as much as possible. This will greatly increase the machine's resilience during the high-intensity tests to come. 9. System integration and prototyping. With all major subsystems, memory, photonic CPU/GPU, QPU, thermal control, self-healing logic, prepared, integrate them into a single prototype. This means mounting components on a common backplane or in a chassis, and establishing all the interconnections, optical fibers or waveguides between the optical processor and memory, high-speed digital links between CPU/GPU and the memory pool, control lines from the classical processors to the QPU, which might be on a separate board or cryostat, and connections from all sensors and monitors to a central management controller. This step will likely surface compatibility issues, timing mismatches between the ultra-fast optical parts and the relatively slower electronic control, or synchronization issues between the quantum operations and classical thread scheduling. Address these by refining the interface logic from step 5, and perhaps introducing buffer stages or adapters, for example, fast FPGA-based transceivers that can translate between optical domain data and electronic bus protocols in real time. At this integration stage, a lot of debugging is done, verifying that the CPU and GPU can indeed access the free-form memory, perhaps testing memory bandwidth to see if optical links deliver the expected throughput, verifying that the QPU can be invoked in a loop from the CPU, testing a simple hybrid algorithm to make sure the quantum cycle and classical cycle align correctly, and checking that thermal sensors trigger the right responses, e.g. artificially heating the CPU to see if the system downclocks it or switches tasks. It's useful to run a set of benchmark scenarios here, for instance, a workload that uses the GPU heavily versus one that uses the QPU, to ensure the system can transition between different modes smoothly. 10. Testing and iterative refinement. Finally, thoroughly test the assembled system under various scenarios, gradually pushing it toward the envisioned operational envelope. Start with theoretical workloads that mirror the intended use, e.g. a simulation that uses the photonic GPU for massive parallel number crunching, then hands results to the QPU for a quantum optimization step, then back to CPU for final aggregation. Measure performance and identify bottlenecks. Perhaps the optical memory isn't fast enough in certain access patterns, or the QPU's qubit coherence time limits the speed of the quantum cycle. Use these insights to iterate. One might upgrade components, e.g. use a faster modulator for the optical link, or improve the cryogenic cooling for the QPU to get more stability, or tweak the software, e.g. deeper pipelining of quantum and classical tasks to overlap their execution. Test the emergency modes by intentionally creating heavy loads, for instance, run a CPU-intensive task and see if the dynamic allocator successfully cuts power to the GPU and boosts the CPU as designed. Induce minor faults, maybe by temporarily disabling a core or introducing a bit error, to confirm the self-healing routines engage properly. Throughout these tests, collect data and compare against expectations. Does the system achieve near light-speed data transfers? Are the bandwidth and latency in line with photonic interconnect predictions? Is the hybrid quantum classical workflow faster than a purely classical one for the target problem? Each round of testing will likely suggest improvements, which can be implemented and tested again. In an academic context, this final step yields the experimental results that demonstrate the viability of the proposed architecture and highlight remaining challenges. The outcome will guide future designs, perhaps leading to a refined second prototype or identifying which technologies, quantum memory, optical RAM, etc., need further development to fully realize the concept. Through these 10 steps, we move from components procurement to a functioning prototype of a radically new computing system. Each step is grounded in current or emerging technologies, showing that while the overall vision is ambitious, it is built upon active research directions in computing. Conclusion. The exploration above outlines a bold vision of a computing device that combines quantum computing, photonic processing, novel memory, and intelligent self-management. The theoretical possibilities are immense. Such a system could perform certain computations orders of magnitude faster than today's computers by leveraging quantum parallelism and light-speed data movement, all while dynamically pushing its hardware to the physical limits when needed. We anchored each aspect of this vision in practical research progress, from quantum memory and hybrid algorithms to optical interconnects and self-healing chips, to show that the gap between science fiction and reality is narrowing. Key challenges remain, of course. Integrating these disparate technologies, each complex on its own, will require overcoming interface mismatches and reliability concerns. Quantum devices are still delicate, photonic processors are still in early stages of commercialization, and managing such a heterogeneous system will demand sophisticated new operating systems or runtime environments. However, if these challenges are met, the payoff is a new class of computing machines that could drive the next leaps in science and engineering. They would be machines where memory is not a passive storage but a dynamic spacetime resource, where processors span different physical realms, quantum and optical, yet work in concert, and where the system can adapt and optimize itself in real time to meet extraordinary demands. In pushing towards this horizon, researchers will likely unlock intermediate innovations that feed back into conventional computing, for example, faster memory architectures or better thermal management techniques for everyday computers. In that sense, pursuing this integrated quantum photonic computing concept is not only an academic thought experiment but also a catalyst for progress in computing at large. Ultimately, the convergence of quantum, photonic, and self-configuring computing represents a compelling path forward as Moore's law slows for traditional electronics. It aligns with the broader trend of heterogeneous computing, using the right tool, or physical phenomenon, for each task, taken to an extreme. The discussion here illustrates how one might theoretically and practically build such a system step by step. While a full implementation may be years away, the steady advances in each constituent technology make it plausible that in a decade or two, we will see early versions of computers that compute with electrons, photons, and qubits together in one platform. Such computers, with free-form memory and dual quantum classical cycles, would mark a fundamental shift in computing capability, opening doors to problems we cannot yet even conceive solving. The roadmap is challenging but increasingly within sight, and the references cited throughout this paper testify to the vigorous research laying the groundwork for this computing revolution. Sources: 1. Dobler, P., and Gitana, M. S. 2025. A Survey on Integrating Quantum Computers into High-Performance Computing Systems. AR14, 2507.03540. 2. Rallis, K. et al., 2023. Hardware-Level Interfaces for Hybrid Quantum Classical Computing Systems. AR14, 2503.18868. 3. Ivesic, M. 2023. Quantum Memories in Quantum Networking and Computing. Post-Quantum Blog. 4. Alexudi, T. et al., 2020. Optical RAM and Integrated Optical Memories, A Survey. Light, Science and Applications, 991. 5. Hamerly, Art et al., 2025. Photonic Computing Takes a Step Toward Fruition. Physics 1884, APS News. 6. Emurian, L. et al., 2014. Computational Sprinting, Architecture, Dynamics, and Strategies. WDDD 2014. Via acg.cis.upenn.edu. 7. Honoroff, M. 2013. How Self-Healing Microchips Recover. Scientific American, March 12, 2013. 8. 2023. AI-driven dynamic power allocation between CPU and GPU for optimal performance and battery life. World J. of ADV, ENG and Tech Sciences, 8, 4, 41-46. Snippet via researcher.life. 9. Peng, B. et al., 2023. Photonic Arithmetic Computing Engine for Ising Problems. Nature Photonics, demonstration covered in APS News above. 10. Light Matter Incorporated, 2024. Photonic Tensor Core Architecture. Technical overview via APS News above.